Okay, how are we going to do this? So I have a bunch of slides I will pop up during the time of the event, during the time of the course. Then there are some materials for the course itself, some Python notebooks and instructions. If you don't have these, let me jump quickly to the repository itself. Help. Stop full screen. And I would just copy these to the chat here as well. So there's a bunch of stuff to install that you can maybe do in the meantime, if you haven't already done it. Oh, here goes. Basically, what you need is Python and a bunch of packages. I think, yeah, should be straightforward to install. I hope these installations, like the instructions, work for them, work for everybody. There's also a link to the slides for future reference if you want to go back to it. But for now, let's go to the slides. Start. So, okay, welcome everybody. Welcome to this small, very basic introduction to ome-zarr and S3 cloud storage. My name is Johannes Soltwedel. Wait, I have this on the next slide. So yeah, my name is Johannes Soltwedel. I'm currently a research software engineer for German bioimaging. I am based in Dresden, Germany. I've been with German bioimaging now for a little more than 3 months. So I started in August. So a very short time ago, I was very new to this entire subject, just like you are now. So maybe we find some common ground here. And my focus area is really anything NGFF, ome-zarr, cloud stuff. And maybe just to give you a bit of context where I come from personally. So I used to work as a bioimage analyst, or actually I'm more a physicist, did some radio oncology in my PhD, and in a follow-up postdoc, I worked as a bioimage analyst at a biophysics institute in Dresden called Physics of Life for about 4 years, where we worked a lot on developing custom image analysis workflows. We developed and maintained some really cool Napari plugins. Look up the Napari cluster plotter, for instance, if you have, like maybe you've seen that before. Contributed a bit to Napari and similar plugins, and supported, or like we try to support people in research data management. We pulled up a small ome-zarr server and tried to get it rolling. And something that we bumped into over and over and over again is, and like I think this is one of the key takeaways from my entire previous work experience, is that any image analysis problem eventually turns into a research data management problem. Because yeah, as you scale up your workflows and try to ingest more image data and standardize your outputs, whatever, you need to start thinking about convention. So, and data transfer, and like eventually you like maybe you start working on your laptop, and at some point you realize, okay, you need something bigger. So you go to the workstation, and at some point you realize, okay, you need something bigger, so you go to an HPC cluster. And every time you kind of have to re-engineer your entire workflows, which is really tedious, which is always comes down to, okay, how am I storing, managing, accessing, organizing my data? And like this problem really came into in very different forms. Like sometimes images were just really, really big. So uh, simple things like wanting to show or collaborate an image were really hard because they would have to like install plugins, get something started, whatever. In the case of in my PhD, I had to do some image registration, which is typically problems like you have two images, image A and B, and you want to, or a moving and a fixed image, and you want to warp the moving image so that it overlaps with the fixed image in a particular way. And there's a bunch of tools, and every tool has a different like convention for how to store these transformations, even if it's just a translation in X and Y, like writing this down in a way that the collaborator understands it, I understand what I did later on, uh, turned out to be really hard. Or other problems like segmentations. You try different things. So sometimes you have file called image.tif, and then you have image underscore labels.tif, then you have image underscore labels underscore cellpost.tif, image underscore labels underscore something. And like this quickly, even though if you're only doing simple things, it turns into a mess. And ome-zarr, I think, will save or already saves a lot of that trouble. And let's start talking about ome-zarr a bit. ome-zarr is, yeah, it's a new file format. And the question is like, why do we even need another one? Maybe some of you know this comic here on the left, this XKCD comic, right? So there's, I don't know, a bunch of competing standards for some data. You say, oh, we need to do something about it. Let's unify all the standards in the one, but everything that you did is just inventing another standard. And from an image format perspective, you may be tempted to think that there's not really a problem here because there's bioformats. I'm not sure if you're familiar with bioformats or what it is. If you never consciously realized you were using bioformats, the chance is really high that you did use it. And bioformats was doing exactly what it's supposed to do, which is handing you data without you realizing actually everything that's going on in the back. And let me just quickly go to the bioformats page just to give you an idea of what bioformat supports. So these are all file format extensions that are supported by bioformats. And you can see I can keep scrolling here for quite a while. There's also some metadata on what features exactly is supported in this file format. And it says bioformats currently supports 155 formats. And I think when I checked a few days ago, it was only 140 something. So there are a lot of file formats out there already, which is nice. And bioformats, right, like helps big time in managing this. So yeah, why do we need another one? And simple answer to that is the format thing has gone a bit out of control, really. So on this plot here on the top right, you can see like the number of file formats that were supported by the bioformats tool, the amount of file formats supported. And in blue, you can see the amount of new file formats being invented. So it seems like the simple existence of the bioformats tool is sort of an incentive to just invent more file formats because, it's going to be supported anyway. And if you invent a new file format, everybody in the image analysis community has done it at some point. You can also go to the bioformats, so the OME team, you pay us amount of money, and then it will be supported. But it really doesn't scale well because maintaining this interoperability and this bioformats tool costs a lot of money. Every night, there is a server that ingests a huge collection of historic image data from all sorts of file formats, make sure everything is still parsed correctly, can be read and write by the bioformats tool, which is a huge effort in maintenance and continuing cost that somebody has to put in and that nobody really pays. So right now, the OME community has done this for the community, but it's getting a bit out of control. And there should be better solutions, really. And that's where NGFF/OME/ZARR comes in. So maybe just to unravel these terms a bit for you, because I found them a bit I'm not sure what the difference between NGFF and ome-zarr is. Is the format called NGFF OME, or what is it? And I think many in the community shared this confusion for some time. And now I think the dust has settled a bit, and it's fair to say that NGFF, which is short for Next Generation File Format, is really the community process of discussing, developing the standard, and ome-zarr is the actual file format that is written to your disk. So ome-zarr is the implementation of the output of the NGFF process, which is also the definition that you find on the NGFF page, which is ngff.openmicroscopy.org. And the NGFF process just roughly is, there's a set of specifications on what and how things have to be written down. And there's a process to follow if you want to make a major change to the standard, which looks pretty much like an editorial process from scientific publishing. You propose something, it's sent to an editor, the editor sends it out to review, the reviewers review your proposal, send you some replies, you get to iterate, major revision, minor revision, hand it in again, etc., until it is adopted and a new version of the spec is published and released. And I think when we talk a bit more about the actual file format, about ome-zarr, there's two important conceptual aspects that I would like you to take away. On the one hand is ome-zarr is a chunked data format. And maybe the The meme here on the left illustrates it a bit. If we work with big microscopy data, you just apply a segmentation workflow, dumps, memory is full. Like if you do GPU stuff, it happens very, very easily. So it's very hard to have your hardware on your device that you're working on keep up with the data that you're working with, because bioimage analysis data can get huge. If you do volumetric EM, whatever, you're quickly outpaced by the data. And conventional file formats like would look like here on the left, underneath this cube. So they are a monolithic file format. So it means it's one file on your disk that can be as large, well, it can be very, very large, 100 gigabytes, terabytes, even whatever. And it's typically structured that you have a header on top. And after the header tells you like how to read and how the data, a bunch of metadata, and then the actual binarized data on your disk. Whereas chunked file formats work very differently. If you were to like inspect the file on your disk, all you would see is a folder with a bunch of subfolders. And each of these subfolders contains tiny proportion of your actual data. So your data is broken down into many, 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 many different pieces. And there's one JSON or YAML or metadata file at the top that tells you where to find stuff, how it is broken down into little pieces, and what structure there is, which has a bunch of pros. Like you can access all these individual chunks in parallel. You don't have to like load everything in memory and then grab the bits from your RAM memory, but you can really just read different parts of the data in parallel from the whole image. Which means also like if your data is already sitting on a cloud and you wanted to look at it, you don't have to download 100 gigabytes just to open an image, but you can really just open it and rather stream than load your data. The con is like if you're working locally and not in a cloud environment, it means your image is not one file, but like potentially thousands, if not 10,000s, or much more chunks or individual files. So like if you want to copy that around, that can get a bit messy, but we're going to talk about that a bit later. And the other conceptual part I would like to take away is the pyramidal structure of ome-zarr. So other image file formats implement this too. And consider like typical whole slide image sections, which can have order of magnitude 30,000 by 30,000 pixels or way more. So this is some data from my PhDs. I think it's a mouse tissue slice. But your monitor, I think mine has only 2,500 by 1,400 pixels, which is, I think, standard ultra high definition. So there's really no point in loading 30,000 by 30,000 pixels into your memory if your computer is only going to be able to show you like a tiny proportion of them. And the solution to that is pyramidal data. So that's a layout of a complex data set that you can represent with ome-zarr. For instance, you can have a plate of data, size order of magnitude a terabyte. And in every of these plates, you can have a bunch of images like in individual wells. And the actual image data is stored in multiple resolution levels. And if you haven't encountered the principle before, this is called an image pyramid. So you have the image in full resolution, which may be a gigabyte, but you also have downsampled copies, like actual copies of the same data along with the data, which gives you the ability that if you zoom out, like on the image here on the left, the computer will only show you the low resolution version of your data because, yeah, your computer screen is not able to display much more anyway. And if you zoom in, it's going to show you the relevant chunks of the high resolution data on your screen. It's a bit like the experience if you browse Google Maps and you zoom out, you zoom in, you see these tiles popping up, like getting lazily loaded on your screen as you navigate the geographical space. And this is a very similar concept. And on top, this is how, like this address here, plate.ome-zarr/row/col/well/image, etc. That would be the actual path of one individual chunk. Exactly. And on the top level of every ome-zarr image, what you also find is a little metadata file that tells you a bit about the layout of the data. So this is really the entirety of the additional value of NDFF. Like some people sat down and actually wrote down how this stuff should be structured and how it should be read. Was that a chat? No. Okay, so yeah, it's just like, yeah, you have the multi-scales, you can have some coordinate systems attached to that. We're going to briefly talk about that later. And you have the data sets, and these entries in the data sets are just like, yeah, the different scales of the image, scale 1, 2, 3, 4, 5. And each of these coordinate transformations field, you would write down, this is the highest scale with a resolution of 1 by 1. The next higher resolution scale would have a resolution of 2 by 2 or pixel size, then 4 by 4, 8 by 8, and so on. And before we dive into S3 stuff, I'm gonna stop sharing here and would ask you to jump into the notebooks. I will also open the repository here. So let me minimize my browser. Yeah, we're already 20 minutes in, so time for some hands-on stuff. Yeah, you can clone this entire repository here, or maybe the easier way is to go to GitHub. In this case, I can do open with desktop. You can download the entire thing as a zip file, load it in your computer, like yeah, clone it to your device, and follow the installation instructions on the front page. Maybe some people, you can give me a quick hands up if you've already done that. Okay, then I'm going to ask differently. Who already has a Python installation on their computer? Yes, cool. Who has cloned the repository? Cool. One thumbs up. Excellent. I'm going to wait another 2 minutes or so to let people catch up with the instructions. I will also copy them to the chat again. I think some people came late and may not have seen them in the chat. Oops. Dude. Here goes. Yeah. Maybe you can give me a quick hands up if you are following the instructions. If you're just sitting in here, enjoying the ride and watch me do stuff, that's also okay. But if you are following along, just to like let me know whether like what pacing is good. Okay, I see 2 hands up. That is good. Yeah. So for the installations, like assuming you already have Python, you just go to any environment, then do pip install UV. UV is a package manager. It's a bit similar to what pip does itself, but it's just much faster. So I like to use it like for quickly setting up repos, destroying them again. These are the commands to clone the repo, navigate into the repo. Oh, wait, I'm not sharing my screen. So just managed to navigate a bit through this on my screen. So yeah, pip install UV. That's the package manager. This is for cloning the environment, cloning the whole repo of the course. This is to create a new environment. And if you use conda before, like this line down here is the equivalent of conda activate, is essentially either for Windows or for Mac. Yeah, feels a bit more codey than the conda activate that many people are familiar with by now. And finally, UV pip install. So UV really just like works like pip. You can just prepend UV every time you do a pip something, and it's just going to be much faster. And then you can start a Jupyter Lab instance to run the notebooks that come with the documents. Okay. Also, feel free, like if any of these like things don't work out, that's what we're here for. We can debug a bit if some stuff doesn't work on your machine. Okay. Part one, saving data as ome-zarr. I'm going to do this in my IDE. Let's jump to the very top. Saving data as ome-zarr. So what I found tricky at first is many tutorials kind of assume that you already have your data in the ome-zarr or it's already somewhere in your cloud. But like, how do you actually like save data as ome-zarr, like starting with nothing? And here in this notebook, there's two ways of doing it with either of two popular libraries. One is called ngvec-zarr and the other one is ome-zarr pi. So the cool thing about this open standard process is that the standard process just tells how metadata has to be laid out, but everybody's free to write their own implementations. And I'm relatively certain that even if all of these file readers like break tomorrow, if you just have the spec, it should be possible to recreate all your data and still be able to read it like in 1,000 years when none of these packages is going to be around, which is, I think, an important part of the process. Yeah, so I have the environment already installed and activated. Let's go. So I'm just gonna import a bunch of packages. Okay, ngfsr. That's my first go-to because it's really simple writing and reading. And to get some image data to work with, let's just go with something simple, cells 3D from scikit-image. Running this command, if you do this for the first time, should trigger some download process. But yeah, you can get this image locally, inspect its shape with image.shape, and you see like it's 60 by 2 by 256 by 256, which means that is probably the amount of set slices. This is, I think, the two different color channels, and these are Y and X. And ngfsr, for instance, brings its own ngf image class. And if you want to like create an ngf image or an ome-zarr image representation in your memory, in your Jupyter notebook, you just like execute this thing. And then you see ngf image is of type ngf image, and it has a bunch of metadata in here that you may or may not have specified. So for instance, the shape, yeah, well, that's as before, 60 by 2 by 256 by 256, the data type, the chunk size, that's important. Like we learned earlier that these images are typically chunked, and that's the size of a chunk. In this case, the chunk is just as large as the whole image, which we're going to change in a second. Then the dimensions I specified are set, then the channel, then Y and X. And I did not pass any scaling information, so I just assumes that the pixel size is 1, 1, 1 along every spatial dimension. There's no translation, so this image is sitting at the origin in space. It has a name that's called cell3D that is specified. I did not specify like what the units of the axis are. I could have also passed like I think it's axis units should be something like maybe set is micrometer. Yeah, thank you, Copilot. And then you see if I execute this again, the axis units. or stored as micrometer for every axis. Okay, cool. If we want to inspect this chunk thing a bit more, let's have a look at an attribute of the image. It's called anti-wave image. And if you want to look for the attributes, you can hit dot. You can see all the stuff that's in there. For instance, the scale. Well, yeah, not very interesting. But let's look at the actual data attribute. So that's a neat feature of Dask. So it gives you this view of your data and tells you there's exactly one chunk, and the size of this chunk is, well, as large as the entire array. So that's a bit boring. Oh yeah, that's what I wrote here. It's a bit boring. So let's make these chunks a bit smaller, so we can actually observe NTFF or ome-zarr in action. And also, for me, I find set the YX a bit unintuitive for viewing. So we're gonna reorder this into channel set YX. So that is first we're gonna make the chunks a bit smaller. So I tell Dask, I turn this image, that's the thing we loaded from SK image above, turn it into a Dask array. Dask is a Python package that does operations lazily. So basically, you can do any sorts of operations on a lazy array, but only if you actually want to look at the data, like display it, save it, whatever. Only then Dask will actually perform the computation that you did. So I call it lazy array, and I say the chunks are 10 by 1 by 64 by 64. So that's to then set the YX order. So I want to have the chunks of size 64 by 64 in XY direction and 10 set slices in one chunk, and also one channel only in one chunk. In the next step, I transpose this array so that channel comes forward first and then set YX. And if you do then, if you execute this, let's have a look at reordered array. You can see this image looks a bit different now. Like it has this array printed on top of it. And the chunks are now 1 by 10 by 64 by 64. Okay, cool. And then we pass this, like, we pass this reordered array thingy again to this toNGFF image function. And if we inspect the NGFF image data attribute, we see, okay, this is actually now represented well in this NGFF image class. The next thing that you have to do before you can actually save stuff to ome-zarr is that you have to convert things into a multi-scales image. Yeah. So the NGFF will automatically create these multiple resolution copies of the image for you if you want. Like, no, if you want. It's kind of a must. And so you use this command here that's called ngFFZAR.toMultiscales. So it takes as input, it takes the ngFF image that you created before and the scale factors. So this could really be, yeah, any sort of scale factors. You can also, this would create two downsampled copies, one by a factor of 2 along every dimension and one by a factor of 4 along every dimension. But you could also specify like multi-different, oh yeah, thank you, Copilot. It could look like this. So that's the scale factor, that would be 1 resolution level. But what I would actually want to have is, give me another resolution level. Oops. So, and one missing curly bracket here. So that's how you could also specify by every dimension. If you wanted, for some reason, you could say like, okay, in this resolution level, I don't want to downsample set again, just XY. So you have a lot of freedom like to work with your chunking scheme and your dimensions, your pyramid scheme. And I think for some applications, like for viewing, is really important, performance-wise. Well, performance-wise, you can find a lot of room for tuning here, like by setting your chunking scheme and pyramid levels accordingly. I'm just going to undo that because I want to keep it simple. So two scale factors, and if I look at this NGFF multiscales image, it gives me a multiscales class with a whole lot of metadata. Maybe that could be improved in the NGFF package, like to have a bit of a nicer view about that. Everybody's still here. Okay. Yeah. So here's a little exercise for you to try. is there a possibility to find the individual scales from every resolution level? And is it possible to find the scale factors? I don't think it's very hard. If you look here in the metadata, it kind of already tells you where to find stuff. Yeah, tip, if you look at ngFF images, multiscales.images, you already see the resolution levels laid out. And then you would have to query those. Okay, I will give you 3 minutes to work on that a bit more, and then we'll just do it together. Also, yeah, feel free to interrupt me at any time, ask questions. Oh yeah, there was a question in the chat before. So Baptiste asked, I get how data is divided in chunks, but how are the different resolutions stored so that we don't just save chunks of every resolution while still allowing fast access? I'm not sure I understand the question exactly. So the chunks, the chunk size is, I think, something relatively universal. So imagine your copies, your multi-resolution copies, as really separate images that are split up into the same chunk sizes. So like, doesn't matter for image pyramid that we just worked with, whether you are looking at image resolution 2 or 4 or at the raw resolution, the chunk size is always going to be 1 by 10 by 64 by 64. That's what we specify. So that's kind of what the viewer, when we start viewing it, is going to stream at a time from the data set, if that makes sense. And of course, like, yeah, setting your chunk size is a really important part, because if you make your chunks too large, it's just going to take a viewer or a reader, for that matter, very long to get the next chunk, while you may have already, dragged the viewer slider to a new plane, whatever. Yeah, so we can store this data in the next step together, and we can have a look on the file explorer and on the browser to see how it actually looks like. Okay, if you are following along, maybe you can give me a sad emoji if it doesn't work for you, like up until this point, be it the installation or something else. Or vice versa, give me a happy emotion if you were able to get to this point. Cool, okay. This works for some people. Then I'm just gonna share my screen again. Let's do this quickly together. So yeah, if I inspect this multiscales.images property, well, this seems to be a list from this square bracket here. And if I look at the first property of it, that is the ngFF image that we've seen before. So like the ngFF multiscales is really just a list of ngFF images, each of which have these properties that we saw before. So you can query the scale, that's the scale factors. Yeah, actually, yeah, that's already the answer. So first element, or if you go into the second element of the list, you can see like it automatically calculated the scales for every level, although I didn't actually specify it further up. Okay, and then I think then we're approaching the last part. There's one command that's called ngFF-zarr or nz to ngFF-zarr, which is basically dumps everything to disk. And I think that the nice part about this package is really actually this function, because it gives you a function to just drop to disk. It doesn't ask you, like, it doesn't come with this zarr syntax so much like other packages, where you have to first create a store, then allocate a group in the store, like one group for every multi-scales, and then fill these groups with stuff. But it's like really the simple function to disk, boom, everything is written out. And just a few important parameters here to note for the store. That's kind of the location on disk where you want to write it. And here, yeah, it's called cells3d.ome-zarr. And the version. The version is important because I mentioned before this NTFS specification is undergoing changes. And there's different versions of the same file format with different metadata that support some stuff or don't. As of now, 0.5 is the latest released version. And yeah, so basically that saves 0.5 ome-zarrs to disk. Let's have a look at that in our browser. So yeah, there's a file called cells3d.ome-zarr. If I go in here, I see this is really just a folder. There's a zar.json where if you look at it, yeah, there's a bunch of information like the axes that I specified earlier, channel ZYX. It gives me the path to all the data sets. That's the raw resolution. That is the next resolution, and this is the last resolution. And I only had three resolution levels. And it also saves a bunch of information on like how it was actually downsampled, like with what tool. In this case, ITK WebAssembly Gaussian filter was used. Cool. If I look into in this folder again, there's a folder called scale 0, an image in there that's called cell 3D. I guess that's one channel. These are two chunks. Because remember, one chunk was of size 1 along the channel dimension. So there's 2 entries here because we have 2 channels, and then there is 4 chunks down in here along for X and Y until you eventually encounter certain information, each of which is an array of size 1 by 10 by 64 by 64. So in this case, one file is 360 kilobytes large. And if we go to the top level, let's also look at the properties of this image. So these are 48 files already for a relatively small file of size 13 megabytes. And yeah, 48 dataset files in 52 folders. So you see, this gets large very quickly. Yeah, I'm gonna skip this here. You can play around with you if you want, like with different chunk sizes. But I think maybe it's more interesting to continue with the cloud stuff. Are there any questions up until this point? Oops, wrong window. Let's stop my sharing quickly. I'm getting an import error for format V05. Okay. If that doesn't work, I think that's something from ome-zarr, like from a package we're not actually using. And I see here that actually I'm not using this at all. So you may want to try just removing this line. Apparently I imported this for an older version of the script and then ended up not using it. Let me share again. So basically, yeah, I can see here it's grayed out. So format V05 from ome-zarr format is actually not used. Yeah. So if you're using the other package, these ome-zarr pi, you kind of have to generate the metadata upfront in particular objects in a particular structure and then pass this to your image writer function. Which is a different way of ergonomics. It gives a bit more control on the one hand, but it's a bit less ergonomic or intuitive on the other hand. Yeah. Hope that we solved. Okay. Yep. Cool. Thumbs up. Then next part is already the cloud part, I think. Part 2, upload to S3. Yeah. Let's talk a bit about S3. Let me go back to my slides. I will share my screen again. I have to hurry up a bit. S3 cloud storage. So S3 is short for Simple Storage Solution, which I think is a really dumb abbreviation. It was first introduced by AWS, which is Amazon Web Services. I think they just developed something for their backend and turned it into a product that they ended up marketing and ended up having I think 80% of the entire internet stored on AWS. And there's just a few important differences to take away. So for once, on local storage, like your data is like on a local hard drive on your machine. On S3 is in a remote cloud file for the cloud infrastructure. On local files, like local storage, data is stored as individual files. And on S3, uh, it's not called files, but it's called objects, which are files with a bunch of metadata attached to it. So the metadata never leaves the file itself. If you're working locally, like you have folders as a hierarchy. And an important thing is on S3, folders don't exist. There's just a long list of files, which, and this is why also these chunks in ome-zarr are so important because the name of a single chunk is really just some words separated by slashes, which locally looks like a folder, but on in S3 storage, it's just a bunch of the individual files, which is fine. If you're working with it locally, like you browse it with a file browser, and if you work remotely, you can stream it with a web browser. If you want to share your data, well, essentially you have to copy stuff on a hard drive, some drives, however, which is costly and time consuming. And S3 and with data on S3, you can just like send somebody URL. If you want to scale storage locally, you just have to buy more hard drive space or allocate more file storage on a network drive. And storage expanding on S3 is really, really easy. Like your IT can just do it for it. Permission-wise, if you want to give different permissions to different places or like different data, like I guess locally you would have to have network drives, give different permissions to different network drives. And on S3, you have data in buckets, which is like the unit of storage for S3. And yeah, let's stop here and actually upload some stuff to S3 before I go rambling about why stuff is so awesome, why this is such a good place to have your data at. Okay, for the next exercise, uploading data to S3, we start on a playground called min.io. Do we go for the playground? Yeah, let me go through it with you real quick. Seems like my daughter is a bit hungry. Okay, let's go through it. We import a bunch of packages again, namely the min.io. Also, I should point out, I said that S3 is like kind of an Amazon thing, but institutions are free to host their own S3-like kind of storages. Like everybody can spin up S3 compatible cloud storage if you don't want to resort to Amazon, which I would prefer. And when you create a bucket, so these access keys should just work. Every bucket has an access key and a secret key, and that's really everything you need to access the data on the bucket, and an endpoint, which is like the host of the host URL of the server. And if you do that, you can use this min.io client to connect to the server. If you want to see, there's a bunch of buckets. Like this is an open playground. These credentials are entirely public. Every Copilot or language model actually knows about them. And let's have a look at the buckets. You can see there is quite a few ones already. So name, whatever, upload, you may want to, like in this case, you can create a new bucket that can have any name. You can try creating test, but that test already exists. So I'm going to create a new bucket that's called cryptic, whatever. You can also go to this homepage and see all the buckets that have already been created. Oops. So once this has been done, I am just creating a small text file. It's called textfile.txt. There's nothing in here. And I'm just going to write the text into this text file. So if we look in here, this has some demo text inside of it. For the sake of time, I think I will skip this exercise and just show you how to use it. So there's this function called client.fPutObject, which essentially is the upload function. So it takes a bunch of arguments like the bucket name, the object name, and the file path. So let me use this function. The bucket name. Yeah, thank you, Copilot. I want to do it myself anyway. So I just call it, bucket name. That's the one I created earlier. The object name is like, how is this file going to be, this object going to be named on my remote bucket? So I choose the same one, text file or text, whatever. And the file path is essentially like, the path to this little text file. And if I run this, it says, oh, that takes a split second, and the data is uploaded. Done. It's that easy to upload to the cloud. And if I go to this playground now, let's do that quickly together. Username and password are these access key and secret key. I need to copy these from here. So that's the access key. And that's the not very secret password. I log in and I see, a ton of buckets that have been created out here. Let's look for the bucket I created. And if I search for this bucket, there it is. There's one text file. Yeah. I could share this now. It would create a link to this file that I could send to anybody, and everybody with that link would be able to have a look at this data. Cool. That's really neat. Vice versa, if you wanted to download the file, there's a function called fgetObject, which works inversely. Like you pass the bucket name, you pass the object file, the object name, and a place locally where you want to put the stuff. So I don't want to overwrite my file. So I'm saving it to a different place. If I run this, another file appeared, downloaded. Yeah, and that's exactly pretty much what I uploaded. Cool. So far, so easy. Let's do this with a more complicated case. Let's upload some image data. So I allocated some S3 storage on a previous employer of mine's IT infrastructure, the TU Dresden. Thank you, TU Dresden. I will invalidate the secret key after this course, so it's like not going to work afterwards. And so I will create this client object to connect to this bucket I allocated. Yeah, cool, that worked. So this, you should be able to just execute. And I now upload all of this stuff to my bucket. So if you want to use it, maybe you create an entirely new bucket of your own, give it some random name, create it, and then you can upload this data. So it's gonna spawn a little progress bar that shows how it's uploading objects. So this is actually, browsing quite a bit of data and upload stuff. So you can see this is already one of the maybe downsides I've mentioned earlier. Like there's a lot of individual files to copy around. And since I'm now not sitting in the network of this institution, like this can become a bit lengthy. Like my connection here isn't super fast. I'm not inside the institution network where all of this would be much faster. Also, I think there's faster clients or faster ways of doing this than from the command line, some of which is written out here on the bottom half of this notebook. This tells you how to do it from the command line, but for the most part, I think that's a relatively stable way to do it. So yeah. I'm also not sitting in my home network. So this is probably a bit slower here than when I tried it last time at home. Okay. Are there questions up until this point? I will just wait another 1 or 2 minutes while this is uploading. I also have this browser here so I can check whether people are creating more buckets here. Yeah, okay. I see some buckets appearing that I definitely didn't create. Awesome. Okay, cool. So I take it you are able to upload stuff to S3 storage. If you are looking at this waiting bar just like me, then I think we can proceed to the next step, which is viewing your data from the web. One neat thing about, like, basically when I used to work with image data, what I always did is like I have a file somewhere, then I open up on the Pari or my Fiji, whatever, drag and drop the file in, view the file, done. So which always required me actually as a prerequisite to have the file locally. But like be able to share the same view or just like show a collaborator what I am seeing was not that easy. And let me share my screen again. ome-zarr data on a remote server serves this, like, I think, in a very neat fashion. There's 2 exercises here that tell you how to open the data in the web browser, but still like from a local representation. But I think the more interesting part here, let's quickly do this. So let's quickly do this from the Napari. I open a new Napari viewer. I think everything necessary should be installed with whatever you downloaded. Or like, yeah, with the environment you installed earlier. And then I run this other command, but you can also drag and drop the ome-zarr image into the viewer. Let's run this. And if I open Napari, you see this. And something that you may notice if you look at this Napari representation is that the contrast values are completely off. This is because Napari ome-zarr, like the reader plugin, will not try to do a good auto scaling, because in order to find good maximum and minimum values for your contrast range, you would have to look at all the data, which is costly. So Napari ome-zarr is just going to assume something and hope for the best, which is not always going to look nice. So if you click on once, this may already be a costly operation, because yeah, if your data is very large, you may have to look at a lot of data to get automatic contrast limits. In this case, I know the data is not very large. So yeah, and if I zoom in and out, maybe if you see me zooming in and out at the edges of the viewer, you can already see this kind of lazy loading scheme, that the data, which shows that the data is only loaded as the viewer goes. If I pan around, you see at the edges that the image is really just appearing wherever I go. Cool, nice. That's an ome-zarr in Napari. That's not very spectacular. Delete again. And yeah, let's do it a different way. Well, let's skip this part and directly go to the web stuff. And one super important page here to keep in mind is the OME NGFF validator. I will return to the part I just skipped later, provided there's time. Let's look at this homepage, what we find here. That is the ome-zarr validator, which is kind of a hub to work with image data. Um, you may be asking like, okay, why do we validate it? But the ome-zarr validator does a bunch of stuff other than validating. And it says, okay, you can just add the URL of the file to the URL of the viewer. Let me just do that real quick. I think I wrote down what the URLs are. So essentially this, the URL of the bucket or of the image is this string here. Maybe it's easier to write it down here. So the complete URL should be, we start with validator and we write down, what was it called? Question mark source equals. Yeah, well. Oh, okay, Copilot is so powerful. So yeah, this is the server where the S3 storage is hosted. This is the internal namespace that is reserved, that you may realize is just my first and last name, Johannes Soltwedel, and some cryptic stuff. This is the bucket name I created earlier, and this is the image, the name of the image on storage. Easy. If I copy this URL, we're probably running into an error. Yeah, which is to be expected, but that is something I can fix real quick in the meantime. Try to follow the rest of the tutorial. So essentially, if you are running into something like a pause error or like couldn't be accessed, whatever, then the problem is that what we are essentially trying to do is we're trying to take a tool from somewhere in the web and let it handle data that is sitting internally at an institution or internally locally at your device. And internet security rules do not permit you to do that, like just out of the box. Like it will not allow tools from the web to just do stuff with your data that you have locally. And the kind of error message that you may be running into is a CORS error, which is short for cross-origin resource synchronization, I think, which essentially tells you, yeah, we have resources from different domains that are not allowed to interact with each other. So I can quickly set this in the settings of the buckets. What was the bucket I created? Let me look into the previous notebook. Add permissions. The one all users can read. Configurations. So I just changed it. Let's run this again. Still not found. Find this file. No. But it's also not the bucket I was working with. My Copilot gave me a nonsensical bucket name. Still not found. Come on. Then I would just use some previously uploaded data. I can copy the links here. Let me share my screen again. And I go now to the browser. It still doesn't affect the file. Okay. Oh, it's wrong. Oh, and it's a double slash here. Ta-da. Okay, cool. Yeah. So that's how it would look like if all the permission stuff has been set correctly. So the NGFI validator, yeah, shows you your metadata, shows you your sizes, and provides you a bunch of icons here that show you like how it can be opened. Like for instance, if you want to use the Allen Wall E volume viewer, let's go there. Spawn. It's gonna load a bit. Ah, cool. And it directly gives us a 3D rendering of our data. And if I zoom in, let's, what else could we do? Take a different coloring. Oh no, dark is always blue. And the cool thing is now, if I hit share here, yeah, I can copy a URL. I can send all of you this URL. Where is the chat? Where is the chat? Here's the chat. And this URL kind of contains everything for this view configuration. So if you open this URL, you should see exactly what I'm seeing. Neat. I think that's pretty cool. There's a bunch of other views as well. Does Neuroglancer work? There's some issues with this data set. I think in this case, it's a bit particular because the data set, the URL has this colon here, which typically is not found in URL. So I think that's something particular to my institution, to the TU Dresden when uploading S3 storage. I think same for ome-zarr. I think I ran into the same problem, but that's going to be fixed soon. Already submitted the pull request to save it, to fix it. But yeah, the Vol E viewer works as well. And I think what's also neat is that you kind of don't have to choose if you work with Apari, you don't have to choose whether you want to have your data locally or on the web, because Apari will also load images if they are on a URL. Oh, that's maybe the wrong one. Let's take this URL that we created down here, s3.zh.udisn, and tell Apari to load this URL. Oh, and I forgot to prepend this bit here. And then I think this is overkill. I think this is wrong. Badly formatted to begin with. Yeah, cool. Yeah, so I'm just passing that as the address of the dataset on the web. And if I open Apari, cool, it's here. So I'm really just, browsing this dataset on the web live. Yeah, and just like to show you something, if I copy this URL, go to the browser. I know that there's a solder.json file at the very top. If I just go there, it will just download it because that's what it's configured to do. Nice. Okay, quick question. Who was able to display something in the OME ngf validator? Can also paste you the URL I was working with into the chat. Cool. Ah, thumbs up. Nice. Okay. Oh, that's awesome. Okay, so you struck it less than I did just now. Awesome. It took me a while to figure this out. I think that some of the concepts were really new to me at the beginning, so glad if it's working for you. Then I will just show you something very quickly before I jump to my last bunch of slides. Let's go to the last notebook. Which is processing remote images. And I think, yeah, viewing and sharing and having it on the cloud is nice, right? But at some point you want to touch your data, work with it, wrangle it through some filters, segment, whatever. And surely you need to have it on your disk for that, right? And the point is, actually you don't. And the more I work with this, the more I realize like having this remotely and not on my local storage makes things quite a bit easier. So let me import a bunch of stuff. And let's load the image with this package called ome-zarr again. So in this case, you don't pass it a remote URL. You can just like the path that you pass to from ngf-zarr can be a URL of on a remote storage, but it can also be a path to your local file folder, whatever. It doesn't matter. And if you run it, you see, okay, cool. You get this multi-scaled objects from before. If you inspect the multi-scales, like let's look at the first ones, and look at the data property, you see, okay, it's the same old image that we uploaded before. It's 2 by 60 by 2560, 2560, 256, 256, and a bunch of different chunks. I think in this case, it chose a bit of a different chunk scheme. So 15 set scales and 128 by 128. And if you plot part of that image, so let's say you choose the highest resolution, you want to choose set plane 30, all the YX slices, and channel 0. If you execute that, you see you get actually a copy of the data is like, yeah, is processed with matplotlib and is shown on your screen, although the data is sitting entirely elsewhere, not on your computer. How cool is that? And here is, if you follow the notebook, here's a link to a much larger data set that I uploaded previously to this course. So if you run this, you see, okay, we're having an image on a remote S3 storage that is about 20K by 20K pixels in 512 chunks that are each relatively large. And it's about a gig of data, as the task information tells you. And let's again plot a part of the data. So pixels 5,000 to 6,000 along every axis. And you see, this is taking actually a bit longer than it may usually do. But this is the overhead of fetching the data, passing it onto matplotlib, processing it. But still, it's not that slow. I guess, like, yeah, if you were to make this larger, let's make it a bit larger. Let's see what happens. This is also going to take longer because task has to fetch more chunks of the ome-zarr from the remote server before being able to plot everything. Yep, and this is what we get. So this is like some bright field images of tiny little microvels on a sample carrier. It's just some data that I happen to work with. And processing works exactly the same. So let's look at this piece of code. So I'm defining here a threshold function. That's called threshold otsu. And it just does, yeah, threshold otsu function from scikit image. It calculates the threshold. It's binarizing the image and it's returning the whole thing as a binary image. And there's this function from Dask array, which is called map blocks, which essentially takes a function and throws it on an arbitrarily large Dask array, on an arbitrary, which can be a remotely stored ome-zarr image, for instance. So in this case, I want to throw this on the entire raw resolution on the entire 20K by 20K image. And if I apply this, it's finished. And the reason why it's so fast is it's not actually executing the data, because you're not looking at the actually return pixel values of the binarized image. But once I do this again, so once I plot, only now the operation that I requested, which is thresholding, is actually executed, and is only executed in this range of pixels. So this helps you to be able to execute really, really complex and large-scale workflows on your laptop in reasonable amounts of times, because you don't always have to throw everything, all the pixels into your machine. But like you can just do stuff on a few pixels, try around without having to stare 5 or 10 minutes at your computer until the next operation is done. And you can then concatenate a bunch of images afterwards. And if you look at this binarized object, is it possible to visualize here? I think so. Okay, I think it's possible to also show the computation graph, which can be like you can throw this image, this binarized image, into yet another function that will just seamlessly execute. Like you could run like, I don't know, connected components labeling on this data, and it will just execute like that. And only once you query the data of this lazy object, the calculation is going to be executed. And this execution can happen locally on your device. It can happen on an HPC cluster. It really doesn't matter. So you can use the same code on all different kinds of platforms while having the data at one place, like which is your cloud storage of your image data. And I think this is like a really neat way to keep the data in one place and like not have to wrangle or re-engineer all your workflows for more complex or higher, like bigger size data sets. And to wrap this off, are there questions first before I jump into my last few slides? Yeah, feel free to just write a few more questions. We can do a little Q&A at the end if you want. So let's go to the slides. Full screen. Oh, I need to share. Okay, cool. Yeah, why is the cloud a good place for your data? And up until this point, I think I have just shown you a new file format, but I hope I can hype you a bit for the stuff that you can do. Because if your data is sitting on a local S3 storage in ome-zarr format, you can do a bunch of really, really cool things with it. For instance, you can link your data into tools like Homero and manage your data. You can collaborate, you can have user groups, you can annotate, write, like draw ROIs or points or whatever, create publication-ready figures, which are essentially views on the data that are sitting on your remote S3 storage. You can, if you want to share your data, as I mentioned before, you can just like, share URLs to your buckets and add these to big repositories, for instance, like to the IDR, or notably also here the OME NGFF challenge, which was a really cool project. So everybody was like asked to convert the data to ome-zarr, like upload a link to a bucket, and that would make it public on this super big repository of a half of a petabyte of bioimage data that can just like, be browsed and reused very, very easily. Then there's tools like the Biofile Finder that make it really easy to search for particular data sets or particular kinds of data sets. And also here, all you need is your data sitting on some S3 storage, and you can just like use it elsewhere. Other people can use it, reuse it, and find your data after all. Then you can access your data in the form of different kinds of viewers. So there's viewers like NeuroGlance, WebNosis, Wall-E, ome-zarr, and a bunch of others. I think there's already quite a vibrant ecosystem of viewers, all of which can just take the data, if configured correctly, from your S3 storage and look at it and annotate it in, I think in WebNosis. You can do bunch of stuff beyond just viewing. But you can still also use your preferred local tools like Safari, Fiji, Big Data Viewer, Mobi, IDK, which is since very recently also Blender. So all of these can work with data if it sits on an S3 storage. And processing your data, I think, can be really, really neat if it's sitting remotely. And if you then dive into workflow engines like Galaxy, Fractal, Nextflow, where you can, in some of these tools, you can just really draw workflows. Like you have workflow steps as blocks and connect these with arrows. And they can just take data from S3, run your workflow on massive data sets of gigabytes, terabytes, whatever. And you can be sitting at your laptop. But you can also still engineer all of this locally on your laptop, if that's where you prefer to work, and like make use of this lazy kind of processing that sits on top of this chunking scheme, which I think is super cool. And I think all of these together is like, for me, a bit the essentials of what makes data and analysis fair. Like your data can be findable, it's accessible in a shared protocol, it's interoperable, many tools and a huge community of tools knows how to ingest this kind of data. It is reusable because it follows the specification. Others can make use of the data for reanalysis, give up a few more citations to your publication where your data came from, which I think is really neat. And yeah, where we really want to go with this format is that the working reality of bioimage analysis or data science in this field is like you sit somewhere with a laptop, but you have access with your fingertips to a lot of resources because your data is just sitting on some cloud storage, and like, yeah, the data can stay close to the compute power, and you don't have to go through these choke points of converting your data to something that you can read, like finding the metadata, keep track of it. You don't have to transfer data somewhere and yeah, sit watching loading bars for hours, which I think is super cool. There's a lot of development effort that is going into this project. There's the spatial data community, which is, I think, working in very close cooperation with the NGFF community. All of this is built on the ome-zarr technology stack, which also gets a lot of funding from big important player like Microsoft, NASA, Google Research. So a lot of institutions are committing resources into this project, which I think gives me confidence that this is going somewhere. And just like to give you a bit of an overview of what's coming next, things that you will be able to do with ome-zarr next. So one thing I mentioned earlier is transforms. So in registration fields, like, you want to kind of store how your images are oriented in space. And the next version of ome-zarr that comes out, hopefully by the end of the year, will give you the possibility to write down images that share some sort of spatial relationship along with the transformation information that tells a viewer of how to transform, rotate, shear, whatever an image so that it looks as you wanted it. So basically, yeah, you can attach all of this metadata to your image data. The next big thing that's coming are zips. So I mentioned earlier that these ome-zarr images can consist of thousands of files, and zip storage essentially allows you to just zip the folder, and viewers and readers will still be able to ingest it as if it were a normal chunked ome-zarr. But it's still a chunked ome-zarr, just like in one zip storage, which is then one file, which is much faster to transfer if you need to. And another big thing is RFC8, which is the collections, which allows you to add all sorts of metadata to your image. So not just the image data, but also tables, meshes, more segmentations, specify the relations between these different pieces of image, pieces of data, which I think is going to be a big change, will give a lot of power to the format and hopefully make a lot of lives easier. Yeah, if you want to know more about the project, go to ngvef.openmicroscopy.org. There are an exhaustive list of tools, viewers, also tutorials, slides for you to dive in if you want to have more insight into any of these building blocks. And at the very end, I just want to acknowledge a few institutions, people. For once, if you've got questions about this later on, go to Image@C. It's really the place to have these discussions. And raise your hand if you say something doesn't work at all. I don't understand this. If you do that, I'm pretty sure or I know from experience that many people will come rushing to your help and help you set this up. And finally, yeah, ome-zarr lives from the contributions of a bunch of very smart people. So I think these are all the attendees of the last OME and GFF hackathons that happened. So yeah, many people contribute to this ecosystem. And I think, yeah, cool. 5 minutes left. Feel free to drop some questions. Thanks. That was really helpful. You're welcome, Baptiste. Yeah, I hope I could convey, especially the S3 storage stuff a bit, because it was, yeah, really a bit arcane for me for a long time, or I just like never had the incentive or opportunity to interact with much with it. One question from Justin. Thanks for the nice question. Yeah, maybe I misunderstood. When you did the binarization remotely and then plotted the 1000 by 1000 patch, was the O2 threshold based only on the 1000 by 1000 patch or the entire image? Well, that's a very good question. I think it is, oh yeah, maybe in this case, also threshold is a bit of a dangerous example. It's happening, I think, on the 1000 by 1000 patch. To be really sure, I guess we could do an experiment and rewrite the function as we did it earlier to not return the binarized image, but to return the threshold value. And depending on what we see, the threshold value should change. Or if the threshold values change on the patch I choose, then it depends on the patch. Yeah. Maybe we can quickly, yeah, maybe I can quickly try that out. And you can ask more questions in the meantime. Let's go here. I do map blocks on sk image dot filters dot threshold O2 and apply this. So what this returns, oh, I think I imported it differently, so it's important. For the threshold value, it's just a task array, so I have to force compute it, which I can do by dot compute. Oh no, and now I applied it to the whole data, not just to a patch. So now I'm applying this to the whole, oof, interrupt, please stop. Yeah, to the whole 20,000 by 20,000 array, which is not good. I just want to have a little patch. What does it contain? Mm, Not sure what's it complaining. Am I using the correct name? Yeah, okay. And I think maybe this case actually threshold also is a bad example because this function kind of wants to give an output that is of the same size as the input. So yeah, it allocates, as you can see here. Yeah, it allocates a 1000 by 1000 output array because that is what it does. Like it turns one array into another. So I guess I would have to, in this case, think a bit about how I could inspect the actual threshold inside there. So yeah, but in this case, if I execute it, then it gets confused because filters.threshold also actually just returns a single value and not a transformed image. Maybe if I add a print statement here. And again, I am applying the compute to the whole image, which is not good. Special value of 0. I'm not so sure about that. But I'm also not sure entirely about the intensity values in the image. But yeah, my guess would be that, yeah, it's the actual, it depends on the patch. Yeah. Oh, more questions? The SIPs development you were mentioning be a solution to working on computing environments where nodes are limited. Nodes, you mean compute nodes? In case you mean compute nodes. Yes. Yeah, exactly. So there's two aspects to this question. So one is SIPs will allow you, yes, to crunch down the number of files from n for large chunking scheme to one file, which, yeah, if you are working in the facility, you want to hand out data to a collaborator, like, or to a customer in an easy fashion, then you have one file to transfer, and like S3 storage will still like be able to understand it. It's just like, yeah, like limiting the transfer overhead. If you Does that answer the question? Another aspect to that is sharding. So that's a feature that's new in 0.5 that I didn't mention earlier. So ome-zarr, which is like doing the underlying block chunk handling, has a feature that's called sharding, which is essentially aggregating individual chunks to, or many individual chunks to meta chunks that then have a common header of these meta chunks. And this allows ome-zarr during the reading and writing to still maintain the same speed as if you have everything like laid out into many tiny chunks, but you have to, like, you can crunch down the numbers of shards, not chunks in this case, to, yeah, by orders of magnitude. I think I've seen examples from data set that would natively consist of millions, if not billions, of chunks, down to a few thousands of shards, which still gives you all the advantages of chunking, uh, but like at much smaller numbers of files. Yeah. Oh, bioimaging North America is appearing. SIPs are planned for winter 2025. Yes. So I've seen the first implementations of this last week in Zurich at the NGWeb hackathon. So I think NGWeb- zarr, there's a development version that can already write out SIPed images. And I think there's also a development version of Napari or ome-zarr, for instance, other viewers that can read SIPed images. But it's not yet officially part of the release. So I hope it can find its way into the next release. But yeah, grain of salt. What is the status? Yeah, good news. Deciding these things and managing is, yeah, it's a community process, which it means cool is a community process, but it also means it can be slow and it can be tedious. But that's our job to help people, usher people along. What is the status of libraries for efficiently importing metadata from classical image file formats? By status mean like development status. So I guess, I don't know, that's how I interpret your question. So you may want to look at the libraries I've shown you are pretty exclusively for ome-zarr, right? There's one notable library also from the Allen Institute, which is called, oh, sorry, bio.io, sending you the link in the chat. Automatically has me going to this page. Yeah, so bio.io is the successor Python library to AICS image.io. By AICS image.io is kind of used to be a bioformats interface, among others, for Python. So that just like gives you a unified API to reading and writing files, irrespective of whether it's CZI or NG2 or ome-zarr, whatever. You can just like read image and then be able to get the metadata out of this out of this red object that you ingested or that you read. And yeah, it natively supports ome-zarr and I think ome-tif as well. And you can kind of then import other plugins for this plugin or for this library. For instance, like bio.io-c-i, bio.io-nd2, whatever, and then this library will be able to provide you with the same reading API or commands in Python, irrespective of whether you're loading ome-zarr or c-i or whatever. Welcome. If there's no more questions, I would conclude this workshop. Thanks for sticking around. And yeah, stay tuned for what's happening next. You're welcome. Links to the slides are on the GitHub. Bye-bye.